You are listening to The Vocal Technologist. Spoken Tech for your ears.
Imagine a platform roughly the size of LinkedIn, right?
Mm.
Processing thousands of requests per second perfectly. And then it just completely freezes.
Where it's a total lockup.
Exactly. A total lockup for like 10 to 15 seconds. Which, I mean, in the world of high availability cloud computing, that is an absolute eternity.
Oh, yeah. It's a lifetime.
Right. And the cause of this, it wasn't a cyber attack. It wasn't, a severed fiber optic cable somewhere. It froze simply because a single underlying digital dictionary reached exactly 58,720,256 items.
Such a specific number, too.
Yeah, it's wild. So welcome to the deep dive. For you listening today, we're going straight into the basement of modern data architecture.
It is great to be here, and we've got a fascinating stack of sources to go through today. We're pulling from two recent editions of the TLDR beta newsletter, specifically the May 25th and May 28th, 2026 editions.
Right.
And this includes some really deep system-level postmortems, tool launches, and basically the architectural theories that are going to define the next decade of data engineering and AI.
Absolutely. And our mission for you today as we go through this is to really explore the hidden physics of data at this staggering scale. We're going to unpack what physically happens to servers when these colossal systems choke,
Yeah.
and how architects are just radically redesigning data pipelines to stop burning astronomical amounts of cache. And I think most importantly, the surprising ways databases are currently mutating, basically, to serve autonomous AI agents rather than human engineers.
Yeah, and what's fascinating here is that, while everyone in the tech world is completely distracted by the shiny interface of the latest AI models, the real revolution, and honestly the real operational risk, is happening in the unglamorous plumbing of data architecture.
Right, the pipes.
Exactly, the pipes. If those pipes can't handle the pressure, or, if they're mathematically inefficient, the AI simply cannot function.
Yeah. Before we can even talk about building reliable AI, we have to look at the physics of those pipes. Because at an internet-level scale, they don't just spring a leak. They burst in highly specific, incredibly expensive ways.
Oh, absolutely.
Which brings me back to that wild production incident at LinkedIn that we saw in the sources. So they have this REST-based service called FishDB.
Right, FishDB.
Yeah. And in production, it was breaching all their availability service level objectives by freezing for 10 to 15 seconds at a time.
Which is just a catastrophic failure cascade just waiting to happen.
Totally. And the root cause was almost absurdly hyper-specific. It was a standard library hash map.
Right.
Basically just a standard way to store key-value pairs in memory. But when it resized at that exact number we mentioned, exactly 58,720,256 keys, everything just halted.
Yeah, and that specific number is actually the key to understanding the physics of memory allocation here. Because at smaller scales, when a system needs to grow a data structure, it just grabs memory from a local heap.
Right? It's super fast.
Exactly. It happens so fast you never notice.
Yeah.
But at nearly 59 million keys, the contiguous block of memory required is so vast that the operating system literally has to bypass the standard heap.
Oh, wow.
Yeah, it has to use a system called MAP.
Wait, let's break that down for a second for everyone. What exactly does MAP do that breaks the system so badly?
So MAP asks the operating system kernel to allocate a massive chunk of memory directly. But to do that safely, it has to acquire a process-wide lock, an EMMA block, in write mode.
A process-wide lock.
Right. It essentially puts a giant padlock on the memory manager for the entire application. So while that massive block of data is being copied over, no other thread in the entire process can do anything related to memory.
Wait, anything?
Anything. It blocks threads that are triggering page faults, meaning, they're trying to access memory not currently loaded in RAM. It even blocks threads calling madvice, which is literally just a way for a program to whisper to the kernel about how it plans to use memory soon.
That is insane. So to put this in perspective, it's basically like a bustling restaurant, right? With hundreds of waiters perfectly coordinating orders and then completely stopping all cooking, all eating, all service for 15 seconds.
Okay.
Just because the host at the front door has to go buy a physically larger reservation book to write down one more name.
That is a perfect analogy. Yeah. The entire asynchronous business logic halts for an administrative task. It's this hidden bottleneck created by the fundamental physics of the operating system.
And the scary thing is, these hidden bottlenecks are everywhere. Like, our sources highlighted another one hiding in plain sight, this time with Apache Kafka.
Oh, yes. Kafka.
Yeah, which obviously powers real-time data streaming for, countless companies.
Yes. Specifically, the article is regarding Kafka share groups. So when engineers want to speed up data consumption, they use share groups to parallelize the work. But the bottleneck just shifts.
Right.
It becomes an issue of tuning specific configurations, particularly this one setting called max.pull.records.
And the default setting for max.pull.records is 500,
Right. Correct.
which intuitively, I mean, that doesn't sound like a dangerously high number to me.
No, it sounds totally reasonable. But at high scale, it causes a highly destructive phenomenon known as greedy capture.
Greedy capture.
Yeah. What happens is a few fast data consumers just grab these full batches of 500 records at once. They end up hogging all the available data in the queue, while the other consumers just sit there completely idle.
Oh, I see.
So your system is technically processing data, but your throughput becomes incredibly volatile. You get these spiky, unpredictable processing times.
So you're basically wasting all that parallel compute.
Exactly. And the fix isn't to buy more servers, it's actually tuning that default setting down so consumers take smaller bites, keeping the whole group continuously busy.
Which is the perfect bridge to another story in our stack. Because, you know, what happens when that chaotic, spiky data throughput hits your cloud data warehouse?
Right.
It triggers crippling, completely unoptimized compute scaling, which is exactly how one engineering manager in our notes ended up staring at a $140,000 Snowflake bill.
A true nightmare scenario for any data team.
Oh,
Cloud warehouses auto-scale to meet demand, so inefficient data ingestion directly translates into evaporated budget.
but the crazy part is, this manager slashed that $140,000 bill down to $38,000 in just 3 months.
Incredible.
A six-figure reduction.
Yeah.
So how do you just surgically erase $100,000 in cloud spend?
Well, it really comes down to attacking the physical layout of the data on the disks. Snowflake's cost hinges on storage, compute, and cloud services.
Okay.
And sure, they right-sized the compute warehouses. They enforced aggressive auto-suspend rules so servers weren't running idle. But the absolute strongest lever they pulled was query design and physical storage layout.
But they didn't just tell their team to, like, write better SQL, did they?
No, they changed how the database engine physically searches for information. They outright banned the habit of using select star.
Because that forces a full scan.
Exactly. It forces the system to scan every single column on the disk. You're burning compute power on data you don't even need. And they also stopped using function-wrapped filters.
That's a function wrap filter.
Like applying a date conversion function inside a search query. Because
Yeah.
doing that completely breaks the database's ability to use indexes. The engine basically has to run the function on every single row before it can even filter.
So you're forcing the CPU to do the work a million times instead of just looking up the answer in a quick index.
Right.
And they also mentioned clustering in the article, right?
Crucially, yes. Clustering sorts data physically on the disk, but it's expensive to maintain because every time new data arrives, the server has to compute exactly where to put it.
Right, it's constantly organizing.
Exactly. So they realized you should only ever pay for clustering if the specific conditions of your daily queries, your predicates, actually match the columns you clustered by. Otherwise, you're just paying to organize a closet you never open.
I love that. You're paying to organize a closet you never open. So whether you're managing cloud budgets or configuring Kafka pipelines, relying on default settings at scale is just silently burning your money and crashing your infrastructure.
Yeah.
You have to understand the physical reality beneath the software.
Exactly. You really do. And that physical reality is currently shifting entirely because of AI.
Oh, absolutely.
If massive data scale forced us to optimize our pipelines, the rise of AI is forcing us to rethink where computation actually happens.
Yeah, and here's where it gets really interesting. Because for the last decade, we've been taught to decouple storage and compute, right?
Right.
Store the data in a database, pull it out, and process it somewhere else. But moving terabytes of data across a network for an AI model to read is just impossibly slow.
Which just physics.
Yeah. So instead of moving data to the AI, we are mutating traditional databases to absorb AI internally.
Yes. And the sources highlighted this huge release called pginfer 1.0.0.
Oh, yeah.
It is an extension for PostgreSQL version 18 and newer. And it literally makes the internal workings of transformer models queryable in standard SQL.
But wait, I mean, that feels entirely backwards from modern architectural trends.
It does, right?
We're cramming the heaviest compute imaginable AI inference straight back into the database storage layer. Why doesn't that just completely melt the Postgres server?
Because of how it's engineered. So Park Infer runs inference efficiently on standard CPUs. It supports heavily optimized bitnet models, and crucially, it can offload the AI inference work to read replicas.
Okay, so it's isolated.
Exactly. You aren't crushing your primary transactional database. You can literally write a SQL query that joins a static table of customer data with a live, real-time AI inference of their sentiment, all without the data ever crossing a network boundary.
That is wild. And the marketing teams mentioned in the sources are already using this to scale AI reliably.
Yes, they are.
They aren't building these fragile tangles of Python microservices anymore. They're managing the state of an AI agent's workflow using standard database ENEMs,
Right, ENM.
which are just rigid, predefined lists of allowed values, and they handle the unpredictable dynamic outputs of AI by dropping them into JSON and B columns, which lets you query unstructured data inside a strict relational database.
The database has basically become the AI engine.
But okay, I have to push back here, because I thought we needed shiny, purpose-built vector databases for everything AI-related. Why are older relational databases or distributed systems like CockroachDB taking over this space?
I think it really speaks to the disconnect between the hype cycle and actual engineering reality.
Hmm.
If you look at CockroachDB, they needed scalable vector search, right?
Right.
A way to search data by semantic meaning rather than exact keywords. But they found that the standard approach the entire industry uses, an algorithm called HNSW, simply did not fit their distributed architecture.
Wait, for those of us who aren't deep into vector math, what is HNSW, and why couldn't CockroachDB just plug it in like everyone else?
Okay, so HNSW stands for Hierarchical Navigable Small World. It basically builds a highly complex, interconnected graph of data points to speed up searches.
Sounds great on paper.
It works brilliantly on a single server, but CockroachDB is designed to be globally distributed across many physical servers. So if you shard an interconnected graph across the globe, traversing that graph to find a result requires thousands of network hops between servers.
Oh, yikes.
Yeah, the latency would be crippling.
So what do? Did they just build something from scratch?
They built their own vector indexing system called CSPAN. It relies on a hierarchical k-means tree, which is just a different mathematical approach. But the brilliant part is how they store it.
Okay.
They don't build a complex external graph. They map the vector index directly into standard relational rows and columns.
Oh, wow. So by disguising the AI index as normal table data, it just magically inherits CockroachDB's existing ability to globally distribute, rebalance, and backup data.
Precisely. They translated an AI requirement into the database's native physical language.
That pragmatic approach reminds me of another long-standing myth busted into the TLDR newsletters today, the so-called JVM tax.
Ah, yes. The deep-seated belief that the Java virtual machine is just inherently too slow and bloated for high-performance analytical workloads.
Right. Because everyone assumes that if you want a fast data tool today, you have to write it in Rust or C++N.
Naturally.
But a benchmark in our sources tested simple vectorized arithmetic kernels running in pure Java and compared them against Ariors, which is written in native Rust. And they matched.
They perfectly matched because the JVM was executing over Apache Arrow buffers.
Okay, what does that mean in practice?
Historically, Java was slow for data because of object overhead and the garbage collector, constantly pausing the system to clean up memory.
Right, those dreaded GC pauses.
Exactly. But Apache Arrow uses off-heap columnar memory. So when you bypass the garbage collector and organize the data cleanly in memory, a warmed-up Java virtual machine does not impose any mysterious tax on raw compute speed.
It proves that if you architect the memory layout correctly, older systems and languages don't inherently hold you back.
Right.
Which brings us to the next, arguably most significant shift. Now that our databases and infrastructure are becoming these AI powerhouses, how do autonomous AI agents actually interact with all this data?
Yeah, that's the big question.
Because how do we build systems where an agent can query your business data without hallucinating, or worse, accidentally dropping a production table?
Well, if we connect this to the bigger picture, this is the core of modern AI risk. One of our sources argued strongly that AI risk is not a modeling problem, it is an architecture problem.
That distinction is so crucial. We spend all our time agonizing over whether a large language model is, smart enough. But the real danger is how we wire that model into the business.
Exactly. The source breaks down the architecture of risk really well. There are 3 mechanism risks: data exposure, incorrect output, and unintended action.
Okay.
And those three mechanisms create 5 very real business harms. You've got brand damage, compliance failure, liability, operational downtime, and commercial loss.
So how do you actually fix that architecturally? If it's not the model, what is it?
You don't fix it by tweaking prompt instructions.
Right.
You fix it with bounded permissions and deterministic validations. You basically build a cage of traditional mathematically strict rules around the non-deterministic AI.
Oh, that makes a lot of sense.
For example, if you want to test an AI for bias, you don't expose real customer data. The sources highlight a library called Mimesis.
Right, mimesis.
Yeah, it creates perfectly balanced synthetic counterfactual data sets.
So instead of a massive privacy nightmare where you're testing on real users, mimesis generates an entirely fake database that isolates a single variable, like maybe changing only the synthetic user's age, to scientifically prove whether the model's output changes based on demographic data.
Exactly. It's a deterministic architectural solution to an AI modeling problem.
Okay, let's unpack this, because building that deterministic architecture is getting complex fast, mostly because of all these new analytics agents popping up everywhere.
Oh, yeah, the landscape is exploding.
We saw a review of 5 open source tools in the newsletter: LangChain, RenAI, LibreChat, and a few others. And the big takeaway was that a slick chat interface doesn't actually matter at all.
Not even a little bit.
What dictates whether an AI agent gives you a reliable answer is the tooling layer underneath, specifically the Model Context Protocol, or MCP.
Because a chat UI is just an illusion of intelligence. An agent needs structured, reliable memory to actually function.
Right.
That's why tools like RushDB 2.0 are launching. They provide what they call agent memory infrastructure. They combine graph storage, which maps how concepts relate to each other, with semantic search into a single layer.
So it gives the AI a structured historical brain, basically.
Exactly.
Which leads to what was probably the most provocative article in our entire stack today. The title was Plan Mode All the Time, Substrate over SQL, and the End of the DE Role.
Yep. The end of the data engineer role.
Are these agents actually replacing human engineers? I mean, really?
Yeah. Well, the role isn't ending. It's blurring entirely. AI agents are fully capable of handling complex data engineering pipelines, provided we use what the author calls plan mode.
Plan mode.
Right. We don't just grant an AI root access and let it run code wildly. We force the AI to output a declarative plan. Then, we validate that plan externally with hard rules, we reset the AI's context so it doesn't get confused by its own history, and only then do we execute.
And the language they use to formulate that plan is changing too. This genuinely surprised me. AI agents actually prefer a format called substrate over SQL.
It makes complete sense when you think about it, though. SQL was invented for human ergonomics.
Right.
It's designed to read like English, select this from that. But an AI doesn't care about English readability. Substrate is a format that conveys the physical algebraic execution plan of a query.
Right. So it's the difference between telling a taxi driver, like, take me to the airport, versus handing them a physical map with the exact GPS coordinates and lane changes required for the route.
Exactly. Agents are just better at processing the physical operations directly. We are literally entering an era where we are designing data systems for agent ergonomics, completely ignoring human ergonomics.
Wow. And part of those agent ergonomics is dealing with the sheer volume of questions these autonomous agents are going to ask.
Absolutely.
Because if you have thousands of agents constantly querying massive data sets every millisecond, the infrastructure will buckle if it tries to calculate perfect to the decimal precision for every single query. We had to trade perfection for speed.
The spade of approximation.
Yeah. The newsletter highlighted this mathematical concept called data sketches. Instead of scanning every single row in a billion-row database to get an exact count of unique users, a data sketch stores a tiny probabilistic sample. The specific mechanism mentioned is keeping only the lowest k-hash values.
Such a brilliant statistical shortcut.
Yeah. Think of it like trying to estimate how many unique authors are in an astronomical multi-story library. Instead of reading every single spine on every floor, you create a rule. You say, I'm only going to write down author names that start with the letters A and B. If you quickly find 1,000 of those, you can mathematically project the total unique authors in the entire library with incredible accuracy without ever checking the rest of the alphabet.
Right, because it trades 100% perfect accuracy for extreme compute savings. For an AI agent needing quick context to make a decision, an answer that is 99% accurate in 2 milliseconds is vastly superior to a 100% accurate answer that takes 10 minutes and costs $20 in compute power.
And the foundational formats of our industry are restructuring to support this exact need for low latency speed. Like Apache Iceberg, which is the dominant format for massive data lakes, is moving to version 4 specifically to handle AI workloads.
Yeah, version 4 is a huge deal.
They're introducing something called one-file commits. By bypassing the heavy, multi-step metadata tree updates that older batch processing systems used, they're dropping query latency down to the milliseconds that an AI agent demands.
Because the infrastructure is shedding its historical weight.
Right.
DuckDB is adding memory extensions like Quack, entirely focused on bypassing the traditional bottlenecks of disk retrieval. Polars 1.41 is bringing faster parquet footer decoding.
Even OpenTelemetry has graduated CNCF as the standard to monitor all this chaos.
Yeah. The entire ecosystem is upgrading its plumbing because the demands placed on these systems by machine-to-machine AI workloads are fundamentally unprecedented.
We have covered so much ground today. We started deep in the weeds with a Rust hash map, freezing an entire server because of a process-wide memory lock at 58 million keys.
Right.
We explored how physically sorting your data on disk can slash a $140,000 cloud bill. We looked at Postgres running transformer models entirely in SQL, proving the database really is the new AI engine.
It absolutely is.
And we explored how mathematical shortcuts like data sketches and languages like Substrate are restructuring data to prioritize robotic efficiency over human readability.
You know, this raises an important question. Something for you listening to critically consider about your own infrastructure today.
Yeah.
If our data systems are now explicitly being optimized for AI agents, meaning the databases literally prefer interacting via physical execution plans like Substrate because human SQL is too ambiguous, what happens when AI eventually starts redesigning its own underlying databases?
Oh, man.
If the architecture evolves entirely for the benefit of machine-to-machine speed, will human engineers even be able to read or comprehend their own company's data pipelines in 5 years? Or will the geometry of our own systems become entirely alien to us?
Wow, that is an incredibly heavy thought to end on. Because right now, you and I can still go down into the basement, trace the pipes, and figure out exactly why the memory locked up. But if the AI rebuilds the plumbing in a language we literally don't speak, well, that is a completely different world. Thank you for joining us on this deep dive. Whether you're managing cloud budgets, tuning Kafka share groups, or trying to rein in an autonomous agent, keep questioning the defaults, keep looking beneath the surface, and keep exploring. We'll catch you on the next one.
Spoken Tech for your ears.